Welcome to Maths with EJD. This is the second video on partial differential equations, which is the partial differential equations playlist is a standalone playlist, but then I'm also adding the videos to the general differential equations playlist. So I think it's important to make this distinction for people to be able to locate some of these videos easily. So in the first video, I talked about introduction to partial differential equations, and we said that partial differential equations have uh, more than one independent variable, all right, and then they can be classified based on the order, based on linearity, and of course they can be classified based on whether they are elliptic or parabolic or hyperbolic. For second order different PDEs in particular, and so you want to refer to the first video to clarify all of that. We gave examples, like real life examples, like wave, heat, and Laplace equations. Okay, so here we want to look at a method of solution focusing on first order partial differential equations, and that is called the method of characteristics. Okay, so the method, that's like an overview, right? The method of characteristics is a powerful technique used to solve first order partial differential equations, PDEs for short. It is particularly useful for solving hyperbolic PDEs or transport equations. That describe the evolution. So I think like wave equation, right, is hyperbolic, if I remember right. So, or transport equations that describe the evolution of some quantity, along characteristic curves, along characteristic curves. That is why it is called the method of characteristics. So the method involves transforming the PDE into a system. So you transform the PDE into a system of ordinary differential equations, all right, which are into a system of ordinary differential equations along these curves, along these curves, along these curves, which can be solved, more easily. Okay, so then we move on to talk about general form. Okay, general form of first order PDE. What is general form of first order PDE? So consider a general first order PDE of the form f of x, y, u, p, q equals 0, all right, where p is partial u, partial x, and q is partial u, partial y, and of course, and u itself is actually a function of x and y is the known function, is the unknown function rather that we are looking for, is the unknown function. Okay. The goal is to find a solution. The goal is to find a solution for u of x, comma y. Okay, that's the goal at the end of the day. Now, let me switch over where as this goes for this, and then we bring in this. So let's talk about method of characteristics, step by step, method of characteristics, which is the focus of this video in particular. So the step-by-step procedure for method of characteristic is to, okay, let me say step one, right? Step one, what do? You write the PDE in characteristic form. Okay, that's where it all starts, in characteristic form. That's why it's called method of characteristics. So here we convert the partial differential equation into a set of characteristic equations, Okay, these equations describe the behavior. These equations describe the behavior of the solution along characteristic curves, Okay, so for a first order PDE, the characteristic curve the characteristic equations rather, the characteristic equations are usually written as, so this is how you write the characteristic equation. So since you're translating partial differential equations into ordinary differential equations, so you have the s to be a of x, comma y, comma u. Then you have the y ds also. The y ds is now b of x, comma y, comma u, while the uds is c of x, comma y, comma u. Okay, so you're making each of both the dependent and independent variables, you're now making them functions. So basically we are saying that x is a function of s. So one of the independent variables is a function of s. Then y is also a function of that s you're bringing up now. At the same time, even the dependent variable u is also a function of that s. That's how it's looking like a parametric kind of thing. If you remember the idea of parametric equations when you're differentiating, right? So that's the kind of deal here. So, but here, what happens? Here, A, B, C are functions that are functions derived from the partial differential equation. And that S, now that parameter, S is a parameter, okay, along the characteristic curve. So S is a parameter along the characteristic curve. Okay, so we are tracing all these parts along the characteristic of S, basically. So the second step now is number 2. After writing in characteristic form, the next thing you want to do is to solve. The next thing is to step 2. Okay, step 2. In step 2, So you solve the characteristic equation. Solve the characteristic equation. Okay. Since now each variable is now a function of s. So it's ordinary differential equation. So you can just integrate directly to get your x, your y, and your s, and your u rather. Okay. Solve the system solve the system of ordinary differential equations along the characteristic curves, along the characteristic curves. So the solution to this system, the solution to this system gives you the gives you the relationship between x, y, and u along the characteristics, Okay, so that goes. Then for number three now, step three. So you can then use initial. So you can use the initial or boundary conditions to get particular solutions, right? So you can get general solutions, but initial or boundary conditions will help you get specific instances called particular solutions. So once you have the general solution, okay, along the characteristics, along the characteristics, okay, you use the provided initial or boundary conditions to find the specific solution, to the PDE. Okay, so that's how that goes. Now we switch over now and this goes green. So let's take example one. I will take two examples to drive the point home. Example one. Okay. So for example one, we'll be talking about linear, we'll have a linear first order PDE with initial condition. Okay. So here, consider the linear first order PDE, partial u, partial x, plus partial u, partial y equals 0. Okay. With the initial condition, u of x comma 0 equals x squared for x belonging to R. Okay. So let's deal with this. In step one, of course, like we've learned already, write the characteristic equations. Write the characteristic equations. Of course, characteristic equations for ordinary differential equations is easily written in form of it's algebraic. It's like usually maybe a quadratic equation, a cubic equation, depending on the nature of the differential equation, right? But here, see how this goes. So this PDE is this PDE is in the form partial u partial x plus partial u partial y equals 0. So the characteristic equations are dx ds equals 1. Of course, we can choose what we want. Then dy ds equals 1. Okay. And du ds is equal to 0. Okay. So we can have it this way. Now, if that is the case, the next thing we want to do, that's step 1. So we have written this, we have broken down. So x is a function of f of, it's more like x of s equals 1, y of s equals 1, and u of s equals 0. Okay. So we are looking at all both the dependent and independent variables. We are seeing them as, as function of a particular s, a particular parameter. Okay. So now we go for step 2. So in step 2, we solve the characteristic equations. Solve the characteristic equations. And in doing that, what do we have? So how do we solve dx ds equals 1? Okay, this is an ordinary differential equation, which can be, we can integrate directly, right? So we can turn that to dx equals ds easily. Okay. And if that is the case, sorry, dx equals ds. So we can just integrate. Dx is equal to ds. So the integral of dx is x. Integral of ds, we can say that's s plus constant c1. Okay. And that's, so here we have x equals s plus c1. So we can do the same for dy ds, which is equal to 1. That means that dy is simply equal to ds, and that means integral of dy is equal to integral of ds. Integral of dy is y, integral of ds is s plus another constant c2, so that we don't use the same constant like before. So again, we can see that since du ds is equal to 0, we can say u is constant. U is constant along the characteristics. That's what that means, because the UDS means the rate of change of U with respect to S. So it means that U is not changing along the characteristics, along the characteristics. Okay. So thus, we can conclude that U now is a function of X minus Y. Okay. So U is finally a function of X minus Y because it's not changing along the characteristics. So here now we now say where F is some arbitrary function to be determined. Okay. And that is why we have the initial condition, right? So we go for step 3, where we deal with the initial condition. So step 3, in step 3, we apply the initial condition. So that will help us take charge of whatever f is supposed to be. So we say that the initial condition is u of x comma 0, which is equal to x squared. U of x, remember we had that in the original equation. So this is the initial condition, u of x comma 0 equals x squared. What this simply means is that in the beginning, when time was 0, okay, when y is 0, right, in the beginning, then it means that x is equal to x squared. Okay, the function is x squared. I think that's basically what the idea is. Okay, so the initial condition is that u of x equals 0 is x squared. So if that is the case, we can substitute. So substituting. So what this simply means is that at that point in time, x is x and then y is 0. So it means that we can make y equals 0, right? So substituting y equals 0 into the solution form, you know, um, into the solution form, we have u of x comma 0. So u of x comma 0 now is now the f of x we got there. We got f of x comma y. So u of x comma 0, that means we have uh yeah, f of x minus 0, because f of x minus y up there, and that is simply equal to x squared. Okay, so this simply tells us that f of x is equal to x squared. We have this much we have this much here, and if f of x is equal to x squared, okay, so we can then conclude that because the function is f of x equals x squared, so step 4, we can get the final solution. So in step 4, the final solution. So we say therefore the solution to the PDE is u of x comma y equals x minus y squared. Don't forget, because we said u of x comma y is f of x minus y. Okay, so, and f of x itself is x squared. So it means that anywhere you see x, you put x minus y. So, and since this is and since this is f of, since this is x squared, right? Okay, so you can now put, instead of x, you have x minus y. So this is what you have. So that's our final solution. So in all, u of x comma y is simply x minus y all squared. And that is what we get in that situation. Okay, so let's take a second example. Now I move over to green here, and then let's go for this. Okay, now example 2. Example 2. So in this case, we're now taking a nonlinear first order, PDE with initial condition. It's initial condition. Okay, so consider the nonlinear first order PDE, which is partial u partial x plus u partial y equals 0. So this is what clearly makes it nonlinear, because we have a dependent variable u multiplied by a derivative of the dependent variable, that's partial u partial y. So that makes it non-linear. Okay, so consider that PDE with the initial condition, u of x comma 0 equals 2x for x belonging to a set of real numbers. So what do we do? Step 1. So for step 1, again, write the characteristic equations. Write the characteristic equations. Okay, write the characteristic equations. So this PDE is in the form, partial u partial x plus u partial y equals 0. Okay, again, now we can say okay, let me switch over this time. The characteristic equations, are, again, we have partial x partial s equals 1. We have partial y partial s equals u, and partial no, not partial, sorry, dx ds is 1, dy ds is u. Okay, u probably because we have this u here, most likely. And then we have partial u, partial s equals 0 because it is constant along the characteristic curve, right? So, so in this case, since you have written out the method of, we have written out the characteristic equations, that we can go for step 2. So in step 2, you solve the characteristics, solve the characteristic equations, solve the characteristic equations. Okay. Now, again, what do we have? Dx, ds. So we have dx, ds equals 1, which implies that dx is equal to ds. And that means the integral of dx is equal to integral of ds. So that means x is equal to s plus a constant c1. We have that. Then we can have dy ds, which is equal to u. So in this case, dy ds is equal to u, totally unconnected. So that means we can have dy, okay, dy equals u ds. So we're integrating with respect to s. So integral of dy equals integral of u ds. Okay, so that means y is equal to us plus a constant c2, like that. So that goes. Then since du ds is equal to 0, so we say u is constant. U is constant. U is constant along the characteristics. U is constant along the characteristics. So if you now say let u, because u is constant now, we can give it so we can say let u be equal to c3. So we now have y, instead of y equals us plus c3, we now have y equals c3s plus c2. Okay, so this is our y now, instead of what we have up there. So then we go for step 3, where we apply the initial condition. So step 3, apply the initial condition. Apply the initial condition. Okay, so again, the initial condition is u of x, comma 0 equals 2x. U of x, comma 0 equals 2x. That's a lot of space. U of x, comma 0 equals 2x. 2x. So we can then say that at y equals 0, we have, at y equals 0, we then have that simply means that u of x of 0 equals 2x. So that means that u of x, comma 0 is equal to, um so u is constant, right? So normally that should be like f of, that should be like okay, at y equals 0, that's what this means. Okay, let me follow this. So at y equals 0, we have that u of x, comma 0 is equal to from here already, right? Y is 0. So if y is 0 already, mm, that means that I'm trying to see what's that? Okay. U of x of 0 equals 2x, right? Okay. We have this. So we can say that u of x of 0 equals 2x. So I'm trying to see how we relate that here, because y is 0. Okay. So that means that and we say that let u be equal to C3. Okay. So at that point in time, u is a constant. So since u is a constant, so this 2x can as well be said to be C3 because it's constant no matter what the value of y is, right? Okay. So we have this expression. So we can say therefore, C3 is equal to 2x. Okay. So substituting this into the equation for y, okay, we get that y, of course, you remember y is actually C3s plus C2. So that simply means that y is now that C3 is 2x, so that's 2xs, okay, plus C2. And this implies that at y equals 0, at y equals 0, right? That means we have 0 equals 2xs plus C2, okay? And that simply means that minus 2xs is equal to C2. So C2 is basically minus 2xs, like that. So in step 4, now we have the final solution. Step 4, final solution. So we can say thus the general solution is u of xy equals 2x. Okay, u of xy equals 2x. Let's see the C2 itself, right? C2 was okay, C2 is granted, and then we have this. Okay, so ux of y is equal to 2x. So this is now the solution. This is the solution to the nonlinear first order PDE. Okay, do I even have to say that? I mean, that's what we're looking for. We've said it that u of xy equals 2x, right? So that goes. In summary, and so can we just summarize everything we have done? In summary, what do we do here? Uh, the method of characteristics involves solving first order PDEs by converting them into a system of ODEs. Okay, the method of characteristics involves solving first order PDEs by converting them into a system of ODEs along characteristic curves, Okay, the steps are as follows. Okay, number 1, write the PDE in characteristic form. Write the PDE in characteristic form. What do you do next? 2, solve solve the characteristic equations. solve the characteristic equations for x, y, and u. 3, apply initial or boundary conditions. Apply initial or boundary conditions apply initial or boundary conditions to determine the solution. Okay, so that goes. So the method simplifies the process of solving PDEs by reducing them to ODEs, making it easier to find solutions along specific curves determined by the characteristics. Through this method, you can solve linear and non-linear first order ODEs, PDEs as demonstrated in the worked examples above. So that's what we have. So can we take some practice? Let's see. Practice. So solve the following, right? Using the method of characteristics. Solve the following PDEs using the method of characteristics. Using the method of characteristics. Characteristics. First of all, you have partial u, partial x, plus 2 partial u, partial y equals 0. I mean, don't forget, it's the same thing as when you say u sub x plus 2u sub y equals 0. It's basically the same thing, okay? So the initial condition here is u of x comma 0 is equal to e raised power x, okay? Then number 2, you have, du dx plus 2 du dy equals 0, where u of x comma 0 is e raised power x. Number 2, you have partial u, partial x plus u, partial u, partial x plus u, partial y equals 0. And you have u of x comma 0 equals x squared. That's number 2. Number 3, partial u, partial x plus 3u, partial u, partial y. This is nonlinear, just like the number 2, equals 0. U of 0 comma y equals 2y. So in this case, x is 0. So mind you, it's going to affect your solution at the end of the day. Then number 4, you have partial u, partial x plus partial u, partial y equals u squared. Also nonlinear because of the u squared. And the initial condition is u of x comma 0 equals 1 plus x. Okay. Then number 5, you have partial u, partial x plus u, partial y, nonlinear because of the u, partial y, equals y. The initial condition u of x comma 0 equals x. Okay, yeah. So that's what we have. You already know the procedure. So let me see your answer in the comment section, either on YouTube or on Facebook. And of course, feel free to let me know if there's a problem you'd like me to solve, or a problem you'd like me to solve, a topic you'd like me to teach. And of course, put your answers in the comment section also, like I said, right? And also let me know how helpful these videos are for you. Then if you have not subscribed to this channel, you'll be missing a lot, because there's a lot on the channel for you to learn, and there's a lot more coming. All right. So you don't want to miss out on that at all. And everybody, don't forget to hit the notification bell so you can always get alerted each time a new video is released. And be sure to like and share so that more people can have access to the great content we have here. Till I come your way again, keep doing maths right. Bye.